Hello everyone, this is the last experiment of your lab 3 course, which is basically a virtual experiment. Okay, so numerical experiment, we simulate the reaction dynamics of CSTR. Okay, we will use the MATLAB code that will be given to you, but we simulate the reaction. Which reaction is production of propylene glycol. Okay, how it is being produced? You react propylene dioxide with water. It gives you propylene glycol. This reaction, we know the kinetics of this is first order reaction. Rate constant with temperature is given to you, the expression, and this is exothermic reaction. So heat of reaction is also given. So what we will do, we will simulate the reaction dynamics, the startup of reaction in CSTR, and later we will see the effect of coolant temperature on reaction conversion. So you have a exothermic reaction occurring in CSTR. Okay, so how we are simulating it? Suppose we have only water in this reactor, and water is one of the reactant, right? Here is the water. So and this reaction is first order with respect to propylene glycol. And zero order is with respect to water. It means water will be used as excess only. Okay, so how we start? We start with water in CSTR completely filled at temperature 25. Okay, then you start giving feed to this of reactants, which is propylene dioxide. Okay, it is coming at a particular feed flow rate and a particular temperature T0, and since the reaction is exothermic, we have the cooling arrangement. We want to control the temperature. So coolant mass flow rate and this temperature in is given. Okay, so now we want to predict the temperature profile with time of the reactor and the concentrations. Okay, for the reactant like propylene dioxide, how it will change with time, or how it will achieve the steady state. Now for that we need to simulate these mathematical model which is coming through mole balance. This is unsteady state. Okay, mole balance for on A, B and C. There is inert here M. Okay, the rate laws, and now with the energy balance we relate temperature with time. So basically you have 1, 2, 3, 4, 5 differential equations, initial value problem, ODEs, and we know the initial conditions. Okay, time t equals 0, we don't have Ca, so Ca is 0. Okay, A basically is your propylene dioxide, B is water, C is your product. Okay, so we move on from here. We have now 5 differential equations, 4 for concentration, 1 for temperature. There are couple differential equations. We will use MATLAB to simulate this one. Okay, here I have given you the how to proceed. Okay, convert this one to M file. So M file is also given to you. This is the MATLAB code. So you will use this one as black box, just as a simulator. So you can take this one. Okay, copy this one and take to MATLAB. Okay, what this? again. Copy this one, close this file. Sorry, you don't do this one. I'm sorry. What do? You open a new M file for this. Okay. Choose new script file. You save this one here. Okay. In editor, and save this file. It will take this name. This is function M file, so this will take same name as here. The file name and this function name has to be same. Save this one. Okay. So your function M file is saved. You have defined your ODEs. Right? Yeah. I will save this one in my MATLAB. Okay. So just you have to focus on this. T0 is the inlet temperature. Okay. Inlet temperature. Okay, we start with 30 feet. Okay, that's fine. TA1 is your inlet coolant temperature. Okay, and we will play with these parameters to see the temperature profile. And here you define all the differential equations. So if you go back, dy is basically dy dt is t comma c. The c is a vector. We have 5 outputs. We need the C1 is the concentration of A, C2 is the concentration of C1, C2 is the for B, and CC is the for the product, and last one C5 is basically temperature. Okay, so now at these conditions we want to know how the temperature will reach the steady state, how the concentration of A, B and C will reach the steady state. Okay, for that you need to run the code. How to run this code is as simple as that. So T comma C ODE15, this is the solver in MATLAB. Okay, one line solver. You take this to command window. Okay, so T comma C, this is the time span you want to run, 0 to 4. Okay, these are the initial conditions. Here 0 for A, this is we started with the water, so there is water in the beginning. Then 0 for C and for product, and temperature is 25, initial temperature. So right now it's solved. So whatever the temperature, the plot you want to generate for temperature or concentration, you can plot. As I said, C1 is the concentration of A, which is propylene dioxide, which is a reactant. So a startup of the CSTR. Okay, how it goes? It goes like this. The feed is coming initially. There is no not much reaction, so it is the concentration is increasing. After some time, reaction dominates. So its reaction starts. It is being converted to the product, and finally it reaches the steady state. This is for reactant A. If you want to see the product, that is C3. Okay, So it will should start with 0. Yep, where's the graph? Here is the graph. So start with 0, there is no product initially, then it is being produced and produced and produced, and then finally it reaches the steady state. Now same we can draw the temperature as I said, it is TC5. Okay, where is the figure? Figure is here. Yes, the initial temperature is 25. There was water only, then you started cooling. So reaction starts, it's generate the heat. So reactor will be heated, so temperature increases, and then finally cooling takes some domination, and in the end it is the balance. So we reach the steady state of temperature. So maximum temperature is going around 80 and it's stabling at around 71, 72. So this is the startup temperature profile for CSTR. Now what about the effect of coolant heat, coolant temperature? Okay, so where is your coolant temperature in the code? TA1. This is the coolant temperature of so if we change this one, suppose we want to analyze the effect on conversion or effect on reaction. Okay, this is 15. The coolant temperature is coming at 15. We saw that maximum temperature it goes around 70. Okay, so if we want to plot a same graph here, okay, you use hold on. Okay, now I will change the coolant temperature. Okay, let's say I make it 5 and then save this one, run the code again. Yes, and again plot T, C5, that is temperature basically. Okay, let me use some different bullet to differentiate. So the second one is for 5. Okay, it is showing something same. It's showing same. I think there is something wrong here. Let me check. Okay, run. Yep, so this code is not taking, so I need to take make add to path. Okay, now go back, do it again. This is okay, so this is the coolant temperature is 5 here. Now I want to plot temperature. Okay, this is the temperature profile. So you can see initially it is little bit decreasing. So coolant temperature is very low. It is cooling the reactor. In the beginning the reaction is not dominating. It's not that much. So it goes down. Then after that reaction take place and it will liberate the heat and the reactor will become hotter and hotter. The temperature rises and then the cooling take place. Cooling take the domination again. The temperature is bringing it. It is bringing the temperature down. So and finally it is reaching the steady state. Okay, I will use hold on and change the inlet temperature, coolant inlet temperature. Okay, make it 15. If I make it 15, save it, again run the code, plot C5. Okay, just change this one, the bullet. Where is my graph? Yep, now you see the final temperature or maximum temperature is changed. If you want to differentiate in the plot, you can use the legend. First one was 5, TA1 equal 5. Okay, the second one was 15, TA1 equals 15. Close. Yep, here you can see the bullet. So TA1 is 15. So this one, when the coolant temperature is higher, of course you will have the higher temperature of the reactor. The cooling is less. So this is your maximum temperature, and the steady state temperature, and the maximum temperature is this. And when you are using a lower temperature, cooler one, the coolant, maximum temperature is this. Makes sense? Okay. How about the concentrations? How about the conversion, you can say? So again, I need to plot for concentration of A, suppose reactant. I will use hold off. I want to get rid of this plot. Okay, better to close this. Now the first one, the inlet temperature is 15, right? TA1, yeah, 15. This one is 15. So hold off. Now plot T comma C1. Okay, C1 is the concentration of A. Yes, this is the concentration. I have explained this one. Now I want to compare what if we change the coolant temperature. Suppose we make it lower, okay, make it 5. So we are using the more cooler coolant, so it will affect the temperature. Okay, now how it will affect the concentrations, the reaction basically. So again we run the code, okay, and then plot C1. Okay, C1, then let us use some bullet for this. Do I have two graphs? Yes, I have two graphs. Okay, the first one was, okay, again let us use legend to make sure which one is which. Legend. So first one was 15. So TA1 is 15 and TA1, the second one is 5. Okay, it's fine. Hope so. So it shows me the continuous line is 15 and this one is 5. So yes, the concentrations, they are different. The final concentration also different. How we can explain this? When we have a cooler temperature for the coolant, it will maintain the lower temperature for the reactor. So lower temperature means lower conversion. Lower conversion means higher concentration of reactant, and that's it. So this is the way you generate your graphs. Look at the report requirements. Okay, I have given different numbers, okay, for different groups, just to make sure that you try by yourself. Okay, and then analyze the effect of each parameters, generate the beautiful graphs and discuss in report, and that's it. So this is the virtual experiment. We tried to simulate a reaction using MATLAB and see the parameters of different effect of different parameters, okay, like coolant or temperature of, we can see also feed temperature in experiment. We can do all these things. So that's why we did this one. I hope you will enjoy using MATLAB or performing this virtual experiment. Thank you.